All right. So we are going to end this week's discussion with the basics of stability. Okay. So we are going to derive certain things here today, and we're going to discuss the term stability used in the context of linear time invariant systems. All right. So again, we have all of us have some idea of the term stability, right? And we're going to formalize our ideas here, and we're going to get rid of a few misconceptions, and also we shall recall that we had some discussion on stability when we studied signals and systems, right? So we are going to bring those knowledge back in here as well. So that's going to be the agenda today. All right. Again, that is the discussion here would be mostly limited to linear time invariant systems. Okay, and then we shall impose the restriction of causality later on. Okay, right. So for the most part, we're going to derive our equations and everything. We're going to discuss everything in terms of linear and time invariant systems. Okay, and then we are going to impose causality. So ultimately, we shall have discussed uh, the condition of stability. Okay, for causal linear time invariant systems. All right. So all right. So I think I would wait for like 1 more minute so that more people can join, and then we're going to start the discussion here. All right. So when I say stability, there are two different types of definition while discussing stability. Okay. All right. So there is one definition which I'm going to tell you right now, rather informally, but you have to understand what I'm going to say here. So you people might be already familiar with the term stability, right? From some other context, right? So let's discuss that, right? Say, imagine this is like a landscape. Okay, this is like a landscape. Maybe this is a mountain profile. Okay, so this is kind of a mountain. This is a valley, for example. This is part of the mountain again. This is a valley. This is again a part of the mountain, and something like that. Imagine something like that. Okay, for a very basic understanding here, right? Now, of course, gravity is working in this direction, right? Gravity is working in this direction, right? Now, say I have some object, maybe a particle or something, some object standing here. I mean, some object that can roll okay, pretty easily, right? So, standing here, right? Something like that. Okay. So now, what happens if I just perturb it? So small change. Okay, so if I perturb it, what happens if I perturb this object slightly? So basically, what if I just nudge this slightly in this direction? What would happen? It will automatically fall, right? What if I perturb this in this direction? So what if I just gently push this object in this direction? What would happen? Of course, because of this particular landscape, this object will fall, right? This object will fall in this direction, right? So yes, we are going to say with that knowledge that this particular point is unstable. Notice very carefully what we are saying here. We are saying that this particular point on the mountain profile here is unstable because since if I put any object here, okay, and if I gently push it, what happens? That object essentially falls from that particular position, right? So we are going to say that, notice very carefully our term here, the term I'm going to use here. I would say that this point is unstable. Very carefully, I'm not saying that this object is unstable. I'm saying that this point is unstable. I'm saying that this point is unstable particularly, right? So if I'm putting certain object here and gently nudge it, it will essentially drop from that point. It will not come back automatically to that point, right? So I'm saying that point is unstable, right? Something like that. Now what if I have an object sitting right here? So what if I have an object sitting right here, right? Now if I just gently push it in this direction, what will happen? It will come back to this position, right? So it will essentially oscillate and it will come back. I am assuming that there is friction here, okay? This is a mountain after all, so there would be friction, right? So this is going to come back, right? So again, if I have this object here and if I push it in this direction gently again, okay, I'm saying slightly I'm perturbing. So the what term is here? Perturb. Perturb means small changes, right? So I'm just gently pushing it. I'm not, I mean, applying a huge amount of force here, right? So I'm just slightly modifying its position. So if I just apply a very small force in this direction again, it will come back to this original position, right? After certain oscillation maybe. Got it? So with that said, I can now say that this point in particular, that this particular point stable. So with this definition of stability, I can say that from a certain state, if I perturb the state and if I then give the object enough amount of time, then if the object can come back to its original state all by itself, then I would say that that particular state is stable. Again, let me repeat. So from this point, if I perturb this object here in either direction, what would happen? This object will automatically move and then again come back automatically by itself to the original position. So this was the initial state and will come back to this state, right? But for this one, if I slightly perturb it, what would happen? It will never come back to the original state by itself. You would have to put some effort to bring it back to this point, right? So this is one definition of stability. And here, while discussing this kind of stability, we are saying that this point is unstable. We are saying that this point is stable. So we are talking about stability of certain points in the trajectory of the particle. So if I let this particle go, then what would happen? This particle will follow this trajectory, for example, right? This path, in a sense. So in this one, we are saying that this particular point is stable, this particular point is unstable, something like that. So we are talking about the stability of certain points in the trajectory of the object, yeah, trajectory of the particle. Again, we're just doing very informal discussion here because this is beyond the scope of your course, okay? This kind of stability is known as asymptotic stability. So the term here is asymptotic stability. Okay, and while discussing asymptotic stability, we discuss stability of the points in the trajectory of a certain particle, right? Something like that. Okay, so asymptotic stability, and asymptotic stability was formally discussed, mathematically discussed by Alexander Mikhailovich Lyapunov, a Russian scientist who actually discussed mathematically properly discussed asymptotic stability. So sometimes the concept of asymptotic stability itself is known as Lyapunov stability. Okay, stability in the sense of Lyapunov. But the point is that we are talking about the stability of different points in the trajectory. Okay, and I'm not going to discuss this further, but I would just mention this term that this point is something called an equilibrium point. This is also something like an equilibrium point in the trajectory of the particle. So I would say that this is a stable equilibrium point. This is an unstable equilibrium point. But again, this is not the part of the discussion today. Okay, this is kind of beyond the course here. Okay, beyond our discussion here. But this concept of asymptotic stability is more general in nature. So you don't have to have a causal linear time invariant system to define this kind of stability on top of it. Right? But the stability we are going to discuss today is known as BIBO stability. So it's called bounded input, bounded output stability. So in short, it's called BIBO stability. BIBO stability. Now, of course, from the context of signals and systems, some of you are already familiar with this term, right? BIBO stability, bounded input, bounded output stability. Now, let me define this formally before we can actually even do anything with it. Okay. Now, this concept of BIBO stability, first and foremost, is applicable to LTI systems only. Okay, so this is kind of applicable to LTI systems only, linear and time invariant systems only. This is defined in this way. Okay, so if for every bounded input, the output of a linear time invariant system is also bounded, then the system is called bounded input, bounded output stable. All right. Now, with that aside, what I mean by this, okay, this is again just to go back. While discussing asymptotic stability, we discussed the stability of the trajectory. Okay, we did not discuss the stability of the system or stability of the object here. Now here, while discussing bounded input, bounded output stability, we discussed the stability of the object itself, of the system itself, right? So we are discussing the stability of the system. Here, in asymptotic stability, we talk about stability of the equilibrium points. So in asymptotic stability, we talk about stability of the equilibrium points. Of the equilibrium points. And here we talk about the stability of the system itself. But again, if you don't understand these equilibrium points and etc., you don't have to right now, because this is kind of beyond the course here, right? Beyond the scope of this particular course here. But you have to understand the definition of BIBO stability. In the definition of BIBO stability, this is what I'm saying. I'm saying that if I have a system, again, it has to be a linear time invariant system, otherwise this definition won't even work. Okay, so I'm saying I have an LTI system. Again, just one more, again, you understand what linear is, right? So if you don't understand what linear is and you are still attending this, that would be unfortunate. And what is time invariant? Just to recap, time invariance is that if I shift the input by a certain amount of time, the output will also get shifted by that particular amount of time. So if I shift the input by 1 second in either direction, the output would also get shifted by the same amount of time in the same direction. That's called time invariance for systems, right? Now, if I have an LTI system, and for our purpose, we are assuming single input, single output LTI system. But again, this idea would be applicable to multiple input, multiple output LTI systems as well. Okay. So again, this is the input. Okay. So input is xt, and this is the output. That output is yt. Now we are saying that if the input is bounded, then the output will also have to be bounded. But look at the wording here very carefully. We are saying that if for every bounded input, the output of the system is also bounded, which again, what is bounded? Bounded essentially means that the signal does not go to infinity at any given amount of time. So I am saying that xt is bounded. We are saying that xt is bounded if the amplitude of the signal is always less than infinity. So essentially it means the amplitude of the signal is always finite, right? The amplitude of the signal is always finite. So essentially that way I would write that the amplitude of the signal is always smaller than a finite quantity. So this is like a finite number. Finite positive quantity, right? So essentially there could be an example of something like this. Say if I say 30. This essentially means that the signal xt, the input, okay, the amplitude of the input never crosses a value of 30, never crosses an absolute value of 30, right? So it is actually bounded bounded between minus 30 and plus 30, something like that. Okay, so it does not go beyond that. So there is a finite upper bound or finite lower bound on the signal. Okay, so essentially the signal cannot go to infinity in terms of the amplitude. If that does happen, then we say that the signal is bounded, right? So that would be an example of this. So that would be an example of this, right? Now, point being that if this is the term here, notice this term very, very carefully. If for every bounded signal, so that is the important term here. We are saying that if for every bounded signal, bounded input, the output is also bounded, then the system is stable. Try to understand this. So if I want to prove that a system is BIBO stable, okay, system is stable in the sense of bounded input, bounded outputness, okay, we would have to figure out every possible input, right? Every possible bounded input. And with every possible bounded input, I have to feed those bounded inputs to the system. And I have to see whether the output is also bounded or not. Do you understand what I'm saying? Okay. So for every possible bounded input, so you can imagine how many bounded signals can you figure out. Of course, there are infinitely many possible bounded signals, right? There are infinitely many possible bounded signals. Okay. So, and if you feed in those infinitely many possible bounded signals to this system, the output is also going to be bounded. If that happens, then you can say that the system is stable. Okay, at least BIBO stable in this sense. Do you understand the point? Okay. So with that definition, it would be very easy for us to prove that the system is unstable. If a system is unstable, it is actually easier for us to prove that a system is unstable than proving a system to be stable. So in this definition, proving stability is slightly more difficult directly than proving instability. Let me give you an example. Let us say that the system yt is simply defined by this. Okay, so essentially it takes the input, it's a static system. Okay, so example of system. Okay, so it's a static system again, it's not a dynamic system, so there is no differential equation involved anywhere. Let's just say that it takes the input, okay, and just gets a reciprocal of that and turns that into the output. So if your xt at a certain point of time is 5, your output is going to be just 1 by 5, something like that. My question is this system BIBO stable? Is this system bounded input, bounded output stable? Now to figure out whether the system is stable, you have to feed in every possible bounded input. And if you can figure out just a single bounded input for which the output is unbounded, then the condition is violated, then the system is unstable, right? It's like just passing a semester, right? In order to pass a semester, for example, you have to pass in all the subjects, right? It's just like that. So in order to pass as a BIBO stable system, it will have to generate bounded output for every possible bounded input. The moment it fails to do so for even for a single bounded signal, bounded input, okay, even if you can figure out a single bounded input such that the output is unbounded, the system is unstable. Just to give you an example, what if I have xt to be equal to 0 here? That would generate an output which is not bounded, right? So if the input is 0, the output is unbounded here. Okay, so this is, of course, 0 is bounded, right? So this is an example of a bounded input, and this is an example of an unbounded output. So I'm saying that we just figured out a bounded input for which the output is unbounded. Try to understand. We just figured out a bounded input for which the output is unbounded. And the moment we figure out even a single example of such, where the input is bounded but the output is unbounded, we can then and there we can say that the system is BIBO unstable. So this system is not stable in bounded input bounded output sense. So am I clear here? So proving instability is way easier than proving stability, right? You just have to find out a single signal for which the signal itself is bounded. So you have to figure out a single input for which the input is bounded but the output is unbounded, and the moment you can do that, you can say the system is unstable. Done, right? So here again we are talking about the stability of the system. Got it? Stability of the system we are talking about. Again, if you have any query, just feel free to ask. Okay. But what if I want to prove that a system is stable, right? If I want to prove that a system is stable, then what can I do? What do I have in my disposal? What can I do? If I want to prove that a system is stable, then I have to check with every possible bounded input, right? And there are infinitely many possible bounded inputs. So I have to feed in every single one of those, and I have to see whether the output is bounded, And if I am done feeding every possible bounded input to the system, and for every possible bounded input, if the output is also bounded, then I would say the system is stable. But doing this is really, really difficult. So of course we need to figure out a better method. Okay. So what is a better method? Of course, a better method would definitely come from the paradigm of mathematics, right? So what can I do? How can I prove stability, right? The question is how to check whether a system is stable. So we checked whether a system is unstable very easily, but how would I check whether a system is stable, right? Do I need to would I figure out a way to feed every possible input to the system? Okay, maybe not. Maybe instead of doing that, someone is asking, okay, there are questions. Okay, I think you did not get the terms properly. Okay, so one of you are asking that whether if I feed in stable input, someone is asking, is it possible to have a stable output with unstable input? So inputs and outputs, the term stability, concept of stability do not apply to inputs and outputs. I think you are talking about bounded inputs and bounded outputs. Someone is saying, I would say the system is stable if even for an unbounded input the output is also bounded. No, that is not the thing. Okay, that is not the definition, right? The definition says a system is BIBO stable if for every possible bounded input the output is also bounded, right? So you cannot check with unbounded inputs, right? So you cannot check with unbounded input. Yes, even if you feed a system unbounded input, it might so happen that the output is bounded, but that's not what we are doing here. Okay, there is another question. Again, someone is calling a system to be bounded. A system is either stable or unstable. Okay, the term bounded is used on signals, and the term stable or unstable is used on systems. Okay, someone is saying, if from the beginning we consider a system to be bounded and then with a single input we can verify that. So no. The point being that if a system is stable, we can only verify that by feeding every possible input to it. Okay, every possible bounded input to it, and checking whether the output is also bounded. Okay, but in order to prove that a system is unstable, if we can just figure out even a single bounded input for which the output is unbounded, then we can say that the system is unstable. Just as this example, if you look at this example, okay, we just figured out a single possible input. Okay, just a single example. We just figured out a single example for which the input was bounded but the output was unbounded, and we just called the system unstable. That is something we can do, right? So even if this condition is violated just for a single signal, we would say that the system is unstable. But in order to prove stability, we have to check with every possible bounded input. Okay, so we have to check for every possible bounded input. We have to check with every possible bounded input. How would I do that? Okay, is there a way? Of course there is a way out through mathematics. Once again, so let's use the mathematics and let's figure out how we can simplify the mathematics for our particular scenario. Once again, we are assuming linear time invariance here. Okay, so we're assuming a linear and time invariant system, right? Now let's say that the input is xt, of course, is the input, and xt is bounded by a certain value m. So m is the bound of the signal. So essentially what I am saying is that if xt is a real signal, I'm not going to write, if xt is a real signal, it would be something like this, but xt could be a complex signal as well. So in that case, it will be the modulus of that smaller than m. Let's not just say. So I'm saying that xt is bounded by an the amplitude of xt is bounded by an upper limit of m. So every possible value of xt for every possible value of time here, okay, this signal never exceeds a magnitude of m. Okay, that's something you have to understand, right? Got it? And say the output is also bounded. Say something like this. We want the output. So we are saying, so we are trying to figure this out. Okay, if we have, if say rather, so this is the input, right? Let's just say this is the input. If this is the input, this should imply that I would have an output. The output I would have, say this is yt is the output. This would imply, if the system is stable, then this would imply that for this input, the output is also going to be bounded, right? And it will be bounded by some other value. But let me just rephrase my statement here properly. Okay, so we are saying for every possible input xt such that xt is bounded, okay, the output yt will also be bounded, and this would be the thing. Okay, now these values m and n are arbitrary, right? As long as the output is bounded, I do not care what the bound is, right? It could be bounded by like an upper value of 10,000. It could be bounded by an upper value of 1 million. It does not matter. This particular value of the bound does not matter as long as it is bounded. As long as the signal is bounded, as long as the signal does not go to infinity, it is bounded. So we do not care about the particular values of m and n here. We just care that the signals are bounded. We just care about the fact that this m and n are positive real numbers. Okay, something like that. We just care about the fact that these numbers are just positive real numbers, right? We do not care about anything else. We do not care about their particular values. We just care about the fact that if the input is bounded, the output has to be bounded as well. Okay, what the exact value of the bound is, we do not care about that. Okay, with that knowledge, let's now figure out how we can check every possible bounded signal, every possible bounded input in a single way, in a single go, right? So let's develop the mathematics behind it. All right, so again, now say we have this system which is a linear time invariant system, right? Got it? And what if I excite the system with a impulse? If I excite the system with an impulse, then the output is known as the impulse response, right? An impulse response is essentially and the transfer function of the system is essentially the Laplace transform of the impulse response. So this GT is the impulse response. Okay, so I am saying LTI system. Now if I take the same system, same LTI system, exact same system, rather let's just copy and paste it. Rather, if I take this exact system, okay, and rather now feed it with some arbitrary input xt. And now what is xt? Xt is the signal that satisfies this condition right now. Anyway, so I know that the output is going to be yt, but I have a proper definition of yt. I have a way of calculating yt because the system is a linear time invariant system. I know that if I know the impulse response and if I also know the output of this, if I also know the input to the system, then I can figure out the output. I can mathematically calculate the output by means of calculating the convolution integral. So we have to integrate this. So essentially the output is going to be a convolution between the input and the impulse response of the signal. So let's just write it differently. So this is the impulse response. If I convolve the impulse response with the input, if I do the mathematical operation known as linear convolution, if I do convolution here, then I would get the output. So if I calculate the convolution of the impulse response with that of the input, then I get the output, right, for a linear time invariant system. Again, this entire thing is dependent on the consideration that the system is linear and time invariant. Otherwise, this whole idea of convolution does not work. So this is convolution, linear convolution rather. All right. All right. So again, question is what is the definition of this? This is the definition. Again, we had a pretty elaborate discussion on this in our classes on signals and systems. So I'm kind of assuming that knowledge here. But again, the definition of this is g tau x t minus tau d tau, something like that. All right. Now I'm going to leave it right now at this point. Let's go back and discuss some, what should I say, preliminary mathematics that you need right now, okay? Let's discuss some preliminary mathematics, okay? Basics. Okay, so let's discuss something called triangle inequality. Okay, triangle inequality, and of course I believe you people already know what triangle inequality is, right? So let's draw a triangle, right? I believe all of you have studied triangle inequality. So let's call this so this is a triangle, right? And it has three sides, right? Let's call this side so of course three sides have three lengths, of course, here. So let's call this side to have a length, what should I say, say this has a length of x1, say this has a length of x2, and this has a length of x3, say something like that. Okay, this has the length of x1, this has the length of x2, this has the length of x3. Now of course from the concept of triangle inequality, you know that the sum of any two sides of a triangle, okay, sum of the length of any two sides of a triangle is greater than the third side. So you can take any two, okay, so you can take any two side, okay, you can take any two sides. So what is the length here? What is the length here? So for example, let's say we are adding x1 with x2, okay, take any two, and that's gonna be greater than x3. Okay, I'm saying greater than equal to because if they are equal to, then it will turn out to be a straight line, something like that. Okay, so the points will be collinear. Okay, take any other combination like x1 plus x3, that would be greater than or equal to x2. So this is called triangle inequality, right? You people know that already. Just to give you the terminal case where this is equal. So if, say for example, x1 is equal to x2 and x3, in that case this is going to be x1 and this is going to be something like x3 and this is going to be x2, so their sum would be equal to x1. So essentially it would, the points would be collinear, right? So that's one thing. So now here, and we have the other case, x2 plus x3 greater than equal to x1. So this is triangle inequality. Triangle inequality essentially says, someone is asking a question, let me just say, if okay, you have a question regarding the boundedness, nature of boundedness. We are going to discuss that. I think after we end the discussion here, your question would be answered. Okay. Okay. Now, this actually assumes some knowledge of real analysis, right? Something you probably have studied. Okay, boundedness of sequences and series and etc. But I'm not going to assume that. But this is kind of true, right? You people already know that triangle inequality, right? Okay. Now say instead of saying this, let's say like this is on a complex plane or something like that. Imagine something like that. Okay, and say that there is a, this is the radius vector for this point. This is the radius vector for this point. This is the radius vector for this point. This is the radius vector for this point, and this is the radius vector for this point. Something like that. Okay, so you can calculate the distances, right? You can calculate the distances. You get it, right? So now, of course, with that said, okay, I mean, do you recall physics, simple physics, vector algebra, right? So many of you do recall vector algebra, I think, right? Okay. Now this length x3, let me just rearrange this to simplify this, because sometimes we can assume these things pretty easily. Let's just say I am, so these are the 3 points, right? Just say these are the 3 points. All right, so we have a triangle here, here, and here, right? All right, so now let's just say that this is the radius vector for this. Okay, and let's just say this is the radius vector for this, and let's just say this is the radius vector for this, and let's just explain everything properly. Okay, so I'm saying that this is radius vector z1, this is vector z2. Of course, these are just complex numbers in our sense. This is z3. All right, just like that. So these are vectors here, pretty simple. Okay, so again, you people know that how do I define the length of this vector? Rather do it this way. Rather, what can I do? Let's define it slightly differently. Okay, again, once again differently. Let's say there is this vector, there is this vector, and there is this vector, right? Let's say this vector is z1. Fine. Okay, say this vector is z2, and then this vector is z3. Okay, now how do you define z3? How do you define z3 in terms of this, the sum of the vector? So how do you define z3? Z3 is the sum of this vector plus this vector, right? Right, from the triangle law of vectors and everything that you have studied probably, right? So I can say that z3 is nothing but z1 plus z2, right? All right, so what about the length of z3, length of this? So that's going to be the mod of this. Mod is essentially a length in this plane here, right? So mod is essentially the length, right? Now with that knowledge, now we also know that the sum of the individual lengths. So what is the sum of this side? What is the length of this side? What is the length of this side? So that's mod z1. What is the length of this side? That's mod z2, right? So what is the, so let's name this. A, B and C. Okay, so if I say what is the length of the side AB, that's mod Z1, right? What is the length of the side BC? That's mod Z2. So length of the side BC is mod Z2. Okay, now what is the length of the side CA? Length of the side CA is mod Z3. But what is mod Z3? Mod Z3 is mod Z1 plus Z2, the whole mod of this entire thing, right? Now, of course, we know that the sum of the individual lengths of any two sides is greater than or equal to the sum of the third side. So if I take the third side to be this CA, this one, okay, then its length has to be less than or at most equal to the sum of these two lengths, right? So what I mean is that we out of this we know that the length of the third side will have to be smaller than the sum of the lengths of the other two sides, or at most it could be equal to, right? Now with that I can say what is C, what was CA? What was CA? CA was mod Z1 plus Z2, right? Mod Z1 plus Z2. And what is this? This is Z1 and plus this is, right? So this is called triangle inequality. Now this is not just true for complex numbers, and this is not just true for two complex numbers. This is true for any number of complex numbers, because this definition is true for any polygon, right? If you have a polygon with n number of sides, then summing the n minus one number of sides, okay, the sum of individual lengths of n minus one number of sides would be greater than the remaining side, of course. So if you have a pentagon, then the sum of the lengths of any four sides would always be larger than the fifth side, larger than the length of the fifth side. So if you have a heptagon, then the sum of the length of any six sides would be larger than the seventh side. So this is true in general. So that way the extension, the possible extension of this is that something like Z1 plus Z2 plus Z3 and so on up to Zn, if I sum those up and take the mod, okay, would be less than equal to the sum of individual modulus. So that's again no longer a triangle inequality, because we don't have a triangle anymore, we have a polygon, okay, but this is still called the triangle inequality because it came from that idea, right? Now let's write it down properly, like a summation, something like a summation. Okay, so this internal thing is a summation, right? So this is like Zi, where I starts from 1 and goes up to n. So it is like Z1 plus Z2 plus Z3 and such, and we have a mod on the whole thing. Now this is less than or equal to, so mod Z1 plus mod Z2 plus mod Z3, something like that. So I would write summation I equal to 1 to n mod Zi, right? So that's the formal mathematical definition of this, right? And of course this is not just true for complex numbers, this is also true for of course any formula that is applicable on complex numbers. By virtue of the fact that real numbers are subsets of complex numbers, that idea would still also be valid for real numbers as well, right? So if these are just real numbers, then that would also be valid, right? Because real numbers are subsets of complex numbers, right? So these are now real numbers. Right? And these summations, again, if these x are like small intervals on a function, then this can turn out to be an integral. So I can have any signal, something like that, and integrate on it, okay, over a certain period, over a certain domain here. Let's just say integrate from a to b, right? And integration is nothing but a summation, right, where the intervals are pretty small, okay, small divided into small intervals. And if I take a mod on that, okay, that would be less than equal to the same integral if I take a mod on the signal and then integrate. something like that. So this is the logical extension of that. Okay, this is part of something called Schwarz inequality. Okay, I mean the extension of this is called a Schwarz inequality, but we are not going to discuss that. This is again for us, this is still the triangle inequality. And this is true in a very intuitive sense. Let me just give you an example. Let's just use our intuition and figure this thing out. Okay, let us just use our intuition and figure this out. Okay, let us just say I have a signal that kind of looks like that, and I want to integrate the signal from this point A to this point B. Let's just say I want to integrate the signal. So I am looking for this integral first, the left hand side, right? So if I integrate this, try to understand what is integral. Integral is essentially area under a curve. So now again, if the area is above the horizontal axis, okay, if the area is above the horizontal axis, then the area is considered to be positive. But if the area is below the horizontal axis, then it is considered to be negative. So this area is negative. Then this area is once again positive, right? So of course the total integral here would be the sum of the areas, right? So again, if I want to integrate this from A to B, and if I integrate this, I integrate the signal xt dt and took a mod, that would just give me the total area here. So these are the plus areas, these are positive areas, and this is the negative area. So these two will be added and this one will be subtracted, and whatever is the result, let's take a mod on that. Okay, let's take an absolute value of that. So that is going to be the result, right? That is going to be the result. Nice. But what if I want to integrate this? Now, what if I want to do the same integration, but now, so again, the blue one is the function, right? So blue one is the signal xt here, right? So this is xt, right? Now, what if I want to do the integration here, but now I want to do the integration in a slightly different way. Let's just say I want to integrate it this way. So I'm going to integrate from A to B, but now I'm going to take a mod on the signal first and then do the integration. Now, of course, what is a mod? Mod is like a rectification. So if the value of the signal is negative, that part will become positive, right? That part will become positive. So this negative part on the signal will now become positive because of that mod here, right? Because of that mod, that negative part of the signal will become now positive, right? So essentially, because of that mod, this part will get reflected and it will become something like that. Now this area which was earlier negative, now this is no longer x. Okay, this is now mod x. We have taken a mod. So every negative part of the area now becomes positive, right? So this is again now a positive part of the area, right? So if I do the integration and then take the mod, then I have negative parts in the area, right? Negative parts in the area. So it will have certain value here. Say for example, if this area is, say for example, say 5, this area is, say for example, 3, and this area is, say for example, -3, then of course the say -4, then the result is 4, for example, here, right? The result is 4. All right. Now here, once I have taken the mod on the signal and then we are doing the integration. So here we have taken a mod on the signal and then we are doing the integration. This area still is 3. This area, this is mod x once again. This area here is still 5. Now this part of the area is no longer a -4, but this is now +4, right? Because of that mod thing here. Now previously this area, this answer was 5 plus 3 and then -4, right? And now here, since I have taken a mod on the signal and then added everything up, because we are integrating after taking the mod, what we are doing essentially, we are adding everything up. So all the negative areas are also becoming positive. So this is like 5 plus 3 plus 4, right? So as you can see, this is going to be always going to be larger than this. So this area will have negative parts in it. So this is always going to be smaller than this. So that is what we have written here. So this is the triangle inequality. So if I take the mod on the signal first and then do the integration, so all the negative areas will become positive. So this is always going to be larger, right? And why is there an equal to sign? Why is there a less than equal to? This could be equal to if the entire signal lies on top of the above the real axis, right? Or below, entire signal lies below the real axis, something like that. Okay. If the entire signal is below the above the real axis, in that case all the areas will be positive. Okay, so all these will have the same sign essentially. Or if the entire signal is below the real axis, then in that case also all the areas will have the negative sign. So after addition you would have a mod and it will be equal, right? But in general this is going to be less than this. Okay, yes, if there is no negative part, then it is going to be equal. So that is why we have this equality, right? So if this signal is entirely negative or entirely positive, then only this is going to be equal, otherwise it will be less. Okay, so I think you get the idea, right? So again, let me just okay. Right? So again, so if the entire signal lies on the positive half here, then this equal to will take hold. Okay, and if the entire signal is below the real axis, below the time axis, so essentially the entire signal is negative, in that case this will also be okay, this will also be equal, right? So our point being that so let's just keep this in mind. Okay, so this is a very important inequality, just you have to keep in mind, and these bounds are any possible bounds, right? Does not matter. So you can integrate from negative infinity to positive infinity, this inequality would still hold. Okay, now let's go back to our discussion earlier. We were saying that the output was, now let's get back to our original discussion. We were saying that we could calculate the output of the system by means of calculating the convolution between two signals, right? So essentially the convolution between the impulse response and the input, and of course this was given by this in integral here. So this is going to be g tau x t minus tau d tau, and we are integrating with respect to tau from negative infinity to positive infinity, right? What were we discussing? We were discussing stability, and our input signal was bounded, and the upper bound was m. It could be 30, 50, 1000, anything. We are not we are not interested about the particular value here. We are only interested about the fact that it is bounded. Xt is bounded. Okay, xt is bounded. Now we are trying to figure out the bound on yt, right? Let's figure out whether yt has a bound or not. If xt is bounded, whether yt is also bounded. If that is true for all possible xt, then we are saying that the system would be stable. Let's just figure out the amplitude of yt. So amplitude of yt is essentially going to be amplitude of this signal. So a mod on this entire integral. So integral from negative infinity to positive infinity, we have g tau x t minus tau d tau, and a mod on this, because that is the thing, right? It's a mod on this, right? But we know from our triangle inequality, so from that we know that this mod of the integral, if I take this is less than or equal to, if I take this integral and bring the mod inside essentially, right? So from our triangle inequality we know that, right? So this is like, this could have negative and positive areas, but this is always going to have positive areas, right? So this is going to be larger than or equal to, right? This is something we already know, right? Okay, got it. Now what about the right hand side here? But what about this one? What about this integral, negative infinity to infinity mod of g tau x t minus tau d tau. Now think about complex numbers. There is one more thing about this. Think about numbers. For example, there is one more thing. I'm not going to prove it. This is very easy to understand. That the mod of z1 times z2 is equal to mod z1 times mod z2, right? And again, something that is applicable directly like this on complex numbers will also be applicable on real numbers. And again, our signals could be complex numbers as well. Doesn't matter really. Okay, so you know this, right? So with that knowledge, we can further simplify this with an equal to sign. And this is a mod on two different signals, mod on a product. So mod of a product and product of mod is the same. So essentially, I can write this. So mod of this multiplied with mod of this, and we have this integral, right? Right, this is like z1, this is like z2. Mod of z1, z2 is equal to mod z1, mod z2, right? And you can verify that anytime you want. Just take any complex numbers, it will be true, right? So something like that we have found, right? So we just figured out that this integral is less than this, and we just figured out that this part on the right hand side is equal to this. So we are saying that the right hand side is equal to this. Got it? The right hand side is equal to this. Got it? No problem with this, I think. Okay. And what about this now? Again, what about this? Now look at this integral very carefully. Okay. So we are saying this is the input, right? This is the input. We know that the input is always bounded by a value of m on the upper bound, right? So this input is always smaller than m, right? So let me just write it down. This is the input, right? This is always smaller than m, right? This is always smaller than m. Let's just write it down like that. This is always smaller than m, right? Right? Always smaller than m. Then what if I multiply this with mod g tau? Then that is always going to be smaller than mod g tau times m. Got it? So this thing, this input was smaller than m. So we wrote that first, and then we multiplied both sides with mod g tau, and then still it remains the same because this is positive, right? After taking a mod, it becomes positive. That is why we have this, right? Got it? Now we can integrate both sides. Integrate both sides, and still, since everything is positive inside, still that's gonna work. See, try to understand. Got it? But what is this m? This m is a constant. So since this m is a constant, it can go outside, right? It can go outside the integral. So essentially, instead of writing this, I would write m integration from negative infinity to infinity. Okay, mod g tau. We have this, so we are going to say, but this is true, right? So now let's go back to our discussion earlier. Let's go back to our discussion. So this was a mod of yt, right? So this was mod of yt. So we just figured out mod of yt was less than this, but this quantity was equal to this, but this quantity is less than this, right? So say this is 1. So just say this is 1, this is 2, this is 3, this is 4. Okay, so the expression 1 is less than equal to expression 2, expression 2 is equal to expression 3, and expression 3 is less than expression 4. So what I essentially have is that expression 1 less than expression 4. Got it? So expression 1 is less than expression 4, right? Because expression 1 is less than expression 2, expression 2 is equal to expression 3, and expression 3, so this is again expression 3. Expression 3 is less than expression 4, so expression 1 is less than expression 4. So what I'm writing is, therefore, mod of this entire thing, negative infinity to infinity, g tau x t minus tau d tau, this integral, that was expression 1, is less than expression 4, which is m times this integral from negative infinity to positive infinity, g tau d tau. Okay, but what is this integral here? That's the mod of the output, right? So this is less than m times this, right? But for stability, for rather BIBO stability, I would say, BIBO stability, this will have to be less than a certain number, right? The output will also have to be bounded. So this number will have to be less than a certain number. Okay? This will have to be less than a certain number. Okay? Try to understand. Okay? So what I am saying is that this could be an upper bound on this. Okay? And since this is smaller than this, I can safely assume that this part is smaller than n, because the idea is that, for example, try to understand, if mod yt is less than 30, then I can always say mod yt is less than 300. Then I can always say mod yt is less than something like whatever, like 10 to the power 100, who knows, 1000, right? So if it is less than 30, then I can put a higher number anywhere here. And yes, I absolutely made a mess. Thank you very much for correcting this. This will have to be a mod g tau. I would have seen that myself automatically. Yes, that is we derived, right? We derived this mod. Thank you for correcting it. So if this is less than, if the output has an upper bound of 30, then I can always say output has an upper bound of, say, something like 10 to the power something, right? I can always say that. And with that definition, I can safely assume that this is also an upper bound on this, right? This is also an upper bound of the upper bound on this. So this is also bounded, right? So m integral from minus infinity to infinity, okay, then integration g tau g tau mod g tau d tau will have to be less than n, right? Will have to be less than n. So try to understand. So this is a finite number. This is a finite number. Finite number. This is also a finite number. So we have an inequality that looks like a finite number multiplied with something and less than finite number. Say, imagine this m is say for example 50. So 50 times this integral, and say I'm saying this is like 100. So point being, since m and n are both finite numbers, this will have to be finite as well, right? This integral will have to be finite, right? This integral will have to be finite. So from this condition, I have to say that this integral have to be finite. So therefore, this integral from negative infinity to infinity on mod g tau d tau will have to be finite. And the moment I have to say, so let's just say should be finite. Okay, should be finite. So just a moment, I'm running out of pages. All right, so this part will have to be finite. And again, once again, the moment I say this will have to be finite, which means it also now has an upper bound, right? This will have to be finite. So the moment we say that, so we are saying that this integral exists. So we are saying therefore this integral minus infinity to infinity mod g tau d tau, and now of course tau is a dummy variable because this is a definite integral. I can just say gt dt, right? Same thing. Okay, should exist, because in order to be finite, in order for the integral to be finite, it first should exist. So this should exist and be finite. So this will have to be smaller than a particular value, right? So we are saying that this integral mod gt must also have its own upper bound. So we are saying that to be q, okay, and that has to be less than infinity, something like that. So this has a proper name. It says that, okay, so we are taking an absolute value. Again, what is gt? The impulse response, right? So we are taking an absolute value on that and integrating it over the entire real line. So in words, it says that therefore the absolute, so therefore the impulse response gt should be absolutely integrable. Absolutely integrable. Yes, I'm just saying that q itself is a finite quantity. Just to write that, I'm just saying less than infinity. So q is a finite quantity, right? So this is a finite quantity. So to say that q is a finite quantity, we are just writing this part. So just to say that this is finite quantity, we are saying that, something like that. So this integral, absolute integral of gt should also have an upper bound. So this is the condition for BIBO stability. So this is, so we are saying this is the sufficient condition rather for BIBO stability. Recall how we started. We started with a bounded input, okay, and we figured out that for any bounded input, the output is also guaranteed to be bounded if the impulse response is absolutely integrable. So a system is BIBO stable if the impulse response is absolutely integrable. So we are just saying uh, a linear time invariant system is BIBO stable if its impulse response is absolutely integrable. Okay, its impulse response is absolutely integrable. If that is so, then the system is BIBO stable. So impulse response is, say for example, gt. Okay, so we are saying that mod gt integrated over negative infinity to positive infinity with respect to t should be finite. So let's just say less than infinity. So it should be finite. That's the point. So that's again a sufficient condition. So it is guaranteed for the system to be stable if this is so. Ask any question you might have. All right. So how do I check stability of a system? Just by making sure, just by checking the impulse response and making sure that the impulse response is absolutely integrable. So if I see for a linear time invariant system, if the impulse response is absolutely integrable, then for any bounded input, the output is also going to be bounded. So that's ensured. Okay. So that's ensured if the impulse response is absolutely bounded, absolutely integrable, right? So that's kind of the definition here. Yes, that is the thing here. So if the impulse response is absolutely bounded, then you can apply any input to the system, any bounded input to the system, output is also going to be bounded. So in other terms, if the impulse response is bounded, sorry, if the impulse response is absolutely integrable, then for any other bounded input to the system, the output is also going to be bounded. Okay? So if you have a system for the impulse response is absolutely integrable, then you can feed any bounded input to the system, output is also going to be bounded, because this is the sufficient condition for BIBO stability, and definition of BIBO stability tells you that, right? Yes, and that is something right now we are going to say. Someone is asking, then it has, does it have a Fourier transform? Absolutely yes. So for a Fourier transform, you know the condition, right? The condition for the existence of a Fourier transform, this was exactly this. Okay, the signal GT has a Fourier transform if this condition is satisfied. So for BIBO stable system, for a stable system, you always have a Fourier transform, right? Right? And if you have a Fourier transform, then you also have a Laplace transform. But for unstable systems, you don't have a Fourier transform, but you have Laplace transforms. Okay? Right? Get the point here. So this is also the condition for existence of a Fourier transform, right? If you recall, we discussed all these things earlier, right? So yes, for BIBO stable systems, they would have the impulse response is Fourier transformable. The impulse response is expressible in terms of sinusoids, right? That's true. That's true. Got it? Now, instead of saying that whether you can calculate a Fourier transform or whether or not you can calculate a Fourier transform, instead of saying things like that, let's just use our concept of Laplace transform and figure slightly more things out about this, right? So I think this discussion is so far has been okay, right? Now, how can we interpret this discussion in terms of the transfer function of a system, right? Because if I have an LTI system, I can always express this in terms of a transfer function. There is just one more thing. If the system is causal, then of course the impulse response is 0 for all t less than 0. So for time, negative time, the impulse response has to be 0 for a causal system. Thus, the condition for BIBO stability becomes, essentially the lower limit becomes 0, right? Because there is no point integrating from negative infinity, because the signal itself is 0 when t is less than 0 for causal system. So if the system is causal, notice very carefully, if the system is causal, then the condition of BIBO stability becomes this integral less than infinity. So if this integral, so essentially we have just changed the lower limit to 0. So that's the condition for BIBO stability for causal system, right? I think that's understandable, right? Now let's think about this in terms of causal linear time invariant system, right? So if I have a continuous time causal linear time invariant system, then we can have a transfer function of that, right? A transfer function description of that. So now let's jump into transfer function. So we have continuous time causal linear time invariant. Okay. So let's say we have a continuous time linear time invariant system, and for our purpose we are assuming single input single output. It does not need to be so, but we are just assuming single input single output for the sake of simplicity here. Okay. So the generalized transfer function is given by GS, and it looks like this. We have a polynomial in the numerator and also a polynomial in the denominator, and polynomial in the numerator kind of looks like this: bm s to the power m plus bm minus 1 s to the power m minus 1 plus and so on b1s plus b0, something like that. And in the numerator we also have a polynomial an s to the power n plus an minus 1 s to the power n minus 1. Then I would have an minus 2 s to the power n minus 2 and so on. And we again discussed all these things earlier. a1s plus a0, something like that. And we call the transfer function rational if the order of the numerator is at most equal to the order of the denominator. So we would assume, in addition to this, that the order of the numerator is less than equal to the order of the denominator. So that's an assumption. It's called a rational transfer function assumption. Again, we are going to discuss these things at a later point. So we're just assuming rational transfer function, rational system rather. For the rational system, the order of the numerator could be at most equal to the order of the denominator. So if the order of the denominator is like 3, the order of the numerator could be 2, 3, 1, 0, anything like that. But order of the numerator couldn't be 4. Okay. So that's an assumption here. Alright. So again, it's a polynomial, it's another polynomial. Now, of course, this is a polynomial, so it would have roots, solutions, right? So we already know the solutions to the denominator's polynomial, the roots of the denominator's polynomial are known as the poles, and roots of the numerator's polynomial are known as the zeros, right? So in the denominator, so it's an nth order system, right? Nth order system. So the denominator's polynomial has an order n, right? So I would have n number of poles. So we would have n number of poles in the system, and let's call them P1, P2, P3 up to Pn. So say these are the poles of the system, and of course the numerator polynomial has an order of m. So then of course the solutions to the numerator's polynomial, rather the roots of the numerator's polynomial, are the zeros of the system. So, and of course, how many zeros would I have? I would have m number of zeros. So I would have m number of zeros. So poles and zeros again. Let me just increase the number of pages. And say the zeros are like z1, z2, z3, and so on up to zm, right? All right. With that said, what I can now do, I can write this as factorized form, in factorized form. So we can say, we can write this out in a factorized form. So we can essentially say, on the denominator, I am saying this is s minus p1, s minus p2, s minus p3, and so on up to s minus pn, because if p1, p2, p3 up to pn are the poles, then of course this can be factorized in this form, right? And here p1, p2, p3 can be real numbers, complex numbers, anything, right? And on the numerator I would also have something like this. In the numerator I would also have something like this. So s minus z1, s minus z2, s minus z3, and so on up to s minus zm. But just one more thing to notice here is that for the denominator I have, what is the highest power of highest power in the denominator? That's s to the power n, right? All the multiplications. But if you do all the multiplications here, you would see that the coefficient of s to the power n is going to be 1. But here the coefficient of s to the power n is an, right? Right? So I would have to multiply this with an, right? To make sure that the coefficient of coefficient of this is something like, coefficient with the highest power is an, right? Similarly, again, if you do the multiplication, the highest power of s is going to be s to the power m, but the coefficient is going to be 1. I have to make sure the coefficient is bm, so I have to multiply this with bm. But again, these are just constant numbers. So this is like bm by an. Okay, so I can divide them and just write this as k. Okay, so that's the final form here. So this is called the ZPK form. ZPK form of a transfer function. So ZPK stands for zero pole gain. K is the gain. So K is the gain here. So it's called the ZPK form of a transfer function, also known as the zero pole gain form of a transfer function. Okay. Now we have this. All right. And once we have this, we can always do a partial fraction expansion on this. Okay. So what would the partial fraction expansion look like? And again, just one more thing, I am saying that all these quantities belong to the set of complex numbers. All these quantities belong to the set of complex numbers. So it could be real numbers, so it could be real poles or zeros, complex poles and zeros. I do not care right now. But I can expand this in terms of partial fractions. And if I do partial fractions, then this is going to be the partial fraction expansion. Some factor divided by s minus p1 plus some factor divided by s minus p2 plus some factor divided by s minus p3 and so on, and then some factor divided by s minus pn. So that's the partial fraction expansion, which is perfectly valid. Again, if you have any query, any confusion, please feel free to ask. Okay. All right, I think this is fine, right? Perfectly fine. All right, so this can be done this way, right? But what is this? What has this been? So this is the transfer function, right? Okay. Now what is the transfer function? So we know that transfer function is nothing but the Laplace transform of the impulse response. And for the sake of stability, the impulse response will have to be a bounded signal such that its integral is bounded, right? So we want the integral, the absolute integral of gt to be bounded, right? So now for that moment, we say, so we have this gs, right? So therefore, if I want to calculate gt, what is gt? Gt is the inverse Laplace transform of this entire thing. That's the impulse response. So impulse response is the inverse Laplace transform of the transfer function of the system. So inverse Laplace transform of this. Question is, what is the inverse Laplace transform of this term? K1 is a constant. Again, K1 is a complex. These K quantities like K1, K2, these things are again complex numbers. Okay, so if I now take the inverse Laplace transform, okay, so this becomes K1 e to the power P1t, right, with ut. I'm not writing ut, I just write ut afterwards. Okay, plus what is the inverse Laplace transform? That's K2 e to the power P2t plus what is the inverse Laplace transform here? That's K3 e to the power P3t and so on up to Kn e to the power Pn with ut. All of them had ut. So ut essentially means that the signal is ultimately causal. Yes, right? But keep in mind, P1, P2, P3 up to Pn, these are not necessarily real numbers. They can be complex numbers, right? So let's have a recap. So if P1, P2, these things, say for example, if P is real, then e to the power Pt is a real exponential, right? So it's either a rising exponential or a decaying exponential based on whether P is positive or negative. And if P is complex, say P is a plus jb, then since p is equal to a plus jb, then e to the power pt will be e to the power a plus jb t. That's going to be e to the power at times e to the power jbt, and which is going to be equal to e to the power at, which is going to be a complex, which is going to be a real exponential multiplied. It could be a decaying exponential, it could be a rising exponential, depending on whether a is positive or negative. And we would have cosine bt plus j sine bt. So this will be an oscillatory term, and this will be either an rising exponential or a decaying exponential, right? So this is an exponential, right? So again, if you recall that we only get oscillations in the response of the system if the poles are complex, right? So essentially for undamped and underdamped systems we only get oscillations. For critically damped system, poles are real, right? For overdamped systems also poles are real, and whenever the poles are real we don't get any oscillatory response because of this, right? Yes, yes. Right, right. So we have this term, right? Now what was our assumption? I want my integral to be I want the integral of this gt to be bounded, right? I want the integral of gt to be bounded. So for BIBO stability, we just proved, for BIBO stability, this integral, again I'm not writing negative infinity, right? Because I'm considering causal systems. This integral will have to be bounded. This integral will have to be finite, right? So this cannot go to infinity. But what is gt? But what is gt? gt is this one, this entire thing. Okay, so let me just copy and paste. So that's gt, that's the impulse response we just calculated moments ago. And I'm not writing ut because ut served its purpose, right? What purpose did ut serve? The purpose of ut was to make the lower limit 0, right, instead of negative infinity. So that is something, right? That is something that must happen, right? Got it? But we know that, rather let's just say so this has to be infinity. Let's just say this has to be infinity, less than infinity. But we know, again from triangle inequality, from inside this, from triangle inequality, let's just say, again we are just doing heavy mathematics today, okay? And I told you that this subject is essentially heavy mathematics. For triangle inequality, we know that this is less than or equal to integration 0 to infinity k1 e to the power p1t plus k2 e to the power p2t plus k3 e to the power p3t and so on to kn e to the power pnt whole thing dt. So that's triangle inequality applied inside, right? Very simple triangle inequality, right? So now I can split this integral into different parts. Like this is going to be equal to integration from 0 to infinity on mod k1 e to the power p1t dt plus integration 0 to infinity mod k2 e to the power p2t dt plus mod integration 0 to infinity k3 e to the power p3t. Instead of saying this, let's just say plus dot 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 plus dot 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 plus integration from 0 to infinity mod kn e to the power pnt dt, right? So that's the integral, right? That's gt, that's this integral, right? So this has to be, so this needs to be less than infinity. So point being, that this entire sum has to be less than infinity. Now you know the nature of infinity. Infinity plus 1 is infinity, right? Infinity minus, say, something like this is still infinity, right? So you can add any finite number to infinity, you can subtract any finite number from infinity, it still remains infinity. So in order for this to be less than infinity, every single part of this will have to be less than infinity, right? So every single part of this will have to be finite. So this has to be finite, this has to be individually finite, all the individual constituent parts will have to be finite. So what I mean is that every single part, like ki e to the power pit, okay, will have to be finite, right? Otherwise, rather, instead of saying finite, will have to be bounded, right? Will have to be bounded. Thus every single constituent parts will have to be bounded. Now look at this. Now this is ki e to the power pit, right? Again, we are assuming this to be a complex number, so we are saying pi to be equal to ai plus jbi, right? So ki e to the power ai plus jbi t, all right, and this can be written as ki e to the power ait times e to the power j bit, and this is going to be ki e to the power ait times cosine bit plus j sine bit, right? Now this is an oscillatory term. This always varies from plus minus 1. This always varies from plus minus 1. This always varies from plus minus 1. But this can become infinity if this term becomes infinity, right? If this term becomes infinity, right? So as time goes on, so time is between 0 and infinity, right? So as time goes on, this could become infinity, right? So if a is a positive quantity, this will become infinity, right? This exponential part will become infinity, which is undesirable here. So as time goes on, okay, this exponential part could become infinity, right? To make sure that that does not happen, so we are saying, okay, this term ki e to the power pit, ki e to the power pit is bounded if, so this part is bounded, right? This part is always bounded. This will have to be bounded, will have to be bounded, right? So this part e to the power ait, so e to the power ait will have to be bounded, right? And now of course, what is this? How can this be bounded? Okay, this can only be bounded if a is a negative quantity, right? ai is a negative quantity. Okay, this will happen if ai, so this ai, so ith coefficient, essentially ith, the real part of the ith pole, right, has to be negative, sorry, has to be negative, right? So if that is negative, then this is bounded. Now let's go back. What we said that for every part here, the real part of every single value here, every single pole here, right, the real part of this p1, real part of this p2, real part of this pn, every single one of them will have to be negative. Thus we are just again doing the same thing. This is this thing, right? So thus mod gt dt integration from 0 to infinity is negative if for every pole pi, the real part of the pole is negative, right? And that is the condition for stability for causal continuous time linear time invariant system. Thus, so what do I mean by the pole being pole having real parts, negative real parts? This means if I draw an S plane, so that's the S plane again, so that's the real part of S and that's the imaginary part of S. Okay, so all the poles will have to be on the negative plane. Essentially, if I have a pole here, pole pair here, for example, okay, the real part of their value is this negative, right? So I can have a system for which all the poles are negative. All the poles are on the left half plane. So this is the left half plane, right? And all the poles must be on the left half plane for stability. So thus we are having this simple definition. Thus for a continuous time causal linear time invariant system, if all the poles are on the left half plane of the left half of the S plane, let's just say that on the left half of the S plane, the system is BIBO stable. So this is an assumption that is often just taught to the students, like the poles should be on the left half plane, done. Okay, this has so much workout behind this. Okay, this has so much proof, so much mathematics behind this, right? Just saying that the poles must be on the left half plane and that is how the system will be stable is really a bad assumption, right? You cannot just say something like that. So this is one of the most important things for causal linear time invariant systems. And of course, we are going to discuss only causal linear time invariant systems throughout this course. So if I give you a transfer function, stability, so here are the few things that you should notice very carefully. Okay, let's say an example. Stability only entirely is determined by the denominator of the system, right? Denominator of the transfer function. So if I give you a transfer function like this, say we have 2s square plus 5s plus 9, and say we have 3s cube plus 16s plus 16s square plus 17s plus 13, something like that. Okay, so whether or not, so it's a third order system, right? And again, you will get the ideas. Why do I call it a third order system? Because the denominator's polynomial is of order 3, right? But why so? Why don't we consider the numerator's polynomial? Because again, the denominator is more important in a way. In terms of stability, the location of the poles will determine the stability of the system. Okay, so what are the poles? What are the poles of the system? Okay, we have this polynomial, but question is, what are the poles of the system? Let's just do our calculation here. Let's just open Python. Okay, ignore this. Okay, import control as ct, something like that. Okay, so let's define the transfer function. G equal to tf, ct dot tf. Okay, what was the numerator? numerator was 259. Okay, okay, right. So the numerator was 259. It does not really matter though. What was the denominator? The denominator was 3, 16, 17, 13. 3, 16, 17, 13. Okay, that's G. Well, hold on. Second. The dark theme doesn't really always work. Okay, so what is the transfer function? This is the transfer function. I think you can see, right? So this is the transfer function. 2s square plus 5s plus 9, or whatever we just considered moments ago, right? So this is the transfer function, right? Right. So you people know how to find out the poles. Sorry. Okay, C dot. Okay. Okay, so that's pole, right? Not the method. What am I doing? G dot pole. Yeah, sure. So these are the pole locations, right? What are the pole locations? These are the pole locations. So we have one real pole and two complex conjugate pole pairs, right? So we have one real pole and two complex conjugate pole pairs, right, for this system. So the poles are at minus 4.224. So poles are at s equal to minus 4.24. Okay, and that's one pole. Another is at minus 0.55 plus 0.85j, minus 0.55 plus 0.85j. Another is at minus 0.55 minus 0.85j. Of course, complex poles would appear in pairs. Now look at the real parts. All of these, so these are the real parts, right? So this is the real part here. This is the real part of the pole. So this is the real pole. Of course, the entire thing is the real part. So this is the real part. All the real parts are negative, right? Right? So the system is stable, right? Why is the system stable? Because all the poles have negative real parts. So it is satisfying the condition that the impulse response will be absolutely integrable. So if all the poles are on the left half plane, the impulse response will be absolutely integrable, and that's the sufficient condition for stability, BIBO stability. So it's BIBO stable, right? BIBO stable. Got it? Simple. Let's take another example. Let's say my transfer function, say, looks like this. Again, the numerator does not matter, right? So I can say whatever I have in the numerator. The location of the zeros won't matter for stability, at least. Okay. So here, let's just say we have s cube minus 3s square plus 15s plus something like that. Okay. So let's just define our system once again. 1 minus 3, 15, 2. Let's just define our system. G equal to dot tf 1 minus 3 1 minus 2, 15, 2. So that's the transfer function, right? Now say calculate the poles. Now what are the pole locations? We have a complex conjugate pole pair and we have a real pole. Of course, it's a third order system, right? We were going to have at least one real pole, definitely, right? So it's okay, let's write down the real pole first. So it's minus 0.13. So the poles are at s equal to minus 0.13 and 1.56 plus 1.56 plus 3.6 j. 1.56 plus 3.6 j. 1.56 minus 3.6 j. Right? So these are the pole locations. So I have at least one pole that's on the right half plane. So we have at least one pole. I'm answering your question shortly. So we have here, so we have at least one pole. So at least one pole on the right half plane. So at least one pole on the right half plane essentially means that at least one of these integrals will diverge. At least one of these integrals will diverge. Means at least one of these integrals will give you an infinity as an answer, right? So if at least one of the poles are on the right half plane, then at least one of these integrals will give you infinity as the answer. And since infinity plus any finite quantity is still infinity, the integral is diverging. So the impulse response is not absolutely integrable anymore. So the system will be unstable. So this system, so unstable. BIBO, unstable. Again, you have questions. In this, we can conclude the transfer function of BIBO state. Yeah, so the idea is that for so one of you are asking, how do I know that there will be one real pole for a third order system? Of course, for a third order polynomial, since it's an algebra thing, right? Since you have a real polynomial, so polynomial with real coefficients, roots can be either real numbers or complex conjugate pairs, right? So if you have a third order polynomial, you are going to have 3 roots. Out of that, you can have one complex conjugate pair, one real root, right? Or you can have 3 real roots. So if you have a third order polynomial, you can have 3 real roots or 1 real, 2 complex conjugate pairs. There is no other possibility, right? And yes, just by looking at the locations of the poles, we can determine whether a system is stable or not. Whether a system is stable or not. But try to understand, we are using a calculator, right? We are using a calculator. But imagine back in 1940s. So if you are in 1940s, did you have a calculator? No. Did you have a computer? No. How would you then solve this? Of course, you would say, I'm going to apply certain numerical methods and figure this out, right? So the point would be to look at this polynomial and solve this polynomial. So so say for example, imagine we are in 1940s, right? So if we are in 1940s, then if I give you this polynomial and this transfer function and ask you to find out the poles, then you'd have to solve this. So s cube minus 3s square plus 15s plus 2 equal to 0. You have to solve this, right? And in order to solve this, you would have to use certain numerical methods. Namely, you could use the bisection method or the Newton-Raphson method, mostly the Newton-Raphson method, to solve this. So you would solve this and figure out the pole locations, right? Figure out the pole locations, and from that you would figure out whether the system is stable or not, right? After all, you want your system to be stable. You don't want an unstable system, right? You don't want to see an unstable system, right? For an unstable system, the output is never bounded. Yeah, something like that. Now here, try to understand that, I mean, doing this for a third order polynomial would be easy. Now consider an aircraft system. I told you earlier that it wasn't uncommon to have a 7th order system, 8th order system, something that big, right? Now again, imagine we are living in 1940s. Now if we are living in 2020, we can use our computer, right? We can use our computer to solve everything, all of these. So even if I give the system a 10th order polynomial, it can still figure out the roots, right? Because it is doing the computation in a computer, right? But manually solving a 10th order polynomial would be very difficult, right? So question would be, so for example, I have a system like this. They have a gigantic system, whatever polynomial, so whatever you write here in the numerator, I do not care. Okay, in the denominator, say I have an 8th order system. Say I have s to the power 8 plus 15 s to the power 7 plus 19 s to the power 6 plus 77 s to the power 5 plus 100 s to the power 4 plus 65 s cube plus 23 s square plus 119 s plus 7. So something like this. Yes, I mean, if I give it to you in an exam, and if you're studying from home, so whatever, right? So I'd say numerator, polynomial, something like that. Okay, and if you are studying from home, of course you can just put it in Python, and Python will give you the answer, right? You will get all the 8 poles, right? If you write down this transfer function in Python and ask for the poles, it will give you all the poles, and by looking at all the poles, you can figure out whether the system is stable or not. That's fine. But imagine you are living in 1940s. Where would you find your computer? You won't have your computer, right? I mean, solving this using Newton-Raphson manually would be a tremendous job. Like, it would take like 20-30 pages, right? So now, next we are going to learn, on the next day we are going to learn a technique that can tell us whether the poles are on the left half plane or not without actually calculating the poles. So on the next day we are going to learn, so that is why the saying goes, necessity is the mother of all invention, right? Out of necessity people invent things. So because it was necessary back then to figure out the stability of such complicated systems without any calculator, right? Without any calculator, people invented techniques that can help in those. See, try to understand. I do not need to know the exact values of the poles in order to know whether the system is stable or not, right? I do not need to know the exact values of the poles in order to figure out whether the system is stable or not. I just need to know whether all the poles are on the left half plane, whether all the poles have negative real parts, right? If that is so, I am happy the system is stable, right? So people invented techniques that wouldn't solve the system, wouldn't figure out the exact location of the poles, but would still be able to tell you whether the poles are on the left half plane or not. If not, then how many poles are on the right half plane, how many poles are on the j omega axis, it will also be able to tell you that. So people invented techniques for doing just that. Not just a single technique, I would say people invented techniques that would tell you whether the poles are on the left half plane. If not, how many poles are on the right half plane, how many are on the j omega axis, without actually calculating the values of the poles. Okay, right? And that is the technique, and those are the techniques we are going to explore starting from our next class. So that will be the end of today's discussion. So I think this was an interesting discussion. So with the very simple thing that for us called causal linear time invariant system that has a transfer function, we can figure out the system's stability just by looking at the location of the poles and just by making sure that all the poles are on the left half plane. But this entire thing came from the very definition of BIBO stability, and we proved this entire thing, right? So again, in many of control system classes in other lectures, teachers do try to avoid this entire derivation, but I don't, so that you have a complete grasp on the ideas, right? Right. So on the next day, we're going to learn a technique, one of the techniques that we can use to figure out the locations of the poles without actually calculating the poles. All right. So that would be the end of today's discussion. If you have any confusion or any question, then feel free to ask. Just keep in mind, if a single pole is on the right half plane, the entire system becomes unstable, right? Because of this integral is ultimately a sum of many integrals. If one of the integrals diverge, the entire sum will diverge. So if a single pole is on the right half plane, the system is unstable. So just saying, even if a single pole is on the right half plane, the system will be unstable. So just that keep in mind. Okay, all right. So that will be the end of today's discussion, and I will see you next week maybe. Okay. So if you have any query, just ask. Otherwise, we are going to end our discussion today. Thank you very much for being patiently waiting here. So we went through a lot of mathematics, lot of complicated mathematics rather, I would say. All right. So maybe I will see you next week, or maybe I will see you after the vacation. All right. So thank you very much. I will see you next week then. Next week or maybe after that.